Chapter 3.4 is about concavity of functions, which is a really important concept. Let's briefly review some terminology. A concave lens has a shape like this, which is actually kind of rare. A convex lens is what you probably think of for like a magnifying glass or something, and that has sides that kind of bulge outwards as light goes like in here and gets focused that way. Where a convex lens, or concave lens, if light comes in here, it actually ends up getting dispersed. I think people say nearsighted people tend to wear these and farsighted people tend to wear those, but I'm not sure about that. All right, let's talk about mathematical shapes. So concave-up is this general shape. There are other examples of concave-up shapes though, and here's a concave-down shape, basically concave-up but flipped upside down. And let's think about what we can say about these shapes and their derivatives and what else is going on. So take a sec to draw what f prime would look like, and I've given an x-axis here. If this was a parabola, its derivative would be what? A straight line, and that straight line would hit the x-axis, would have an f prime of 0 at the local minimum here, and over here the slopes are positive. Actually, we could kind of draft those in with some positive slope tangent lines. So we'd have something like that. Here's f prime, and over here the slopes are negative. So we could have some tangent lines over there. So that's what f prime would look like for this concave up shape. For the concave down, you can imagine the same basic thing, but standing on its head. There's my tangent lines, and f prime, if this was a parabola, f prime would be linear and would hit 0 here where the concave down function has a maximum. And then what about the second derivative? Try to sketch in the second derivative of all this. Well, what's the derivative of a positively sloped line? It's just whatever the slope is, which is positive. So I'm going to do that in a pencil. And, oh, got too hasty there, huh? What's the second derivative of this negatively sloped line? It would be a constant negative value. So take a sec to think about what are the various ways we could define concave up and concave down mathematically in terms of the derivative or the second derivative with tangent lines or any other kind of behavior, and then we'll write down a bunch of those. All right, last time I taught this, I asked my class for some ideas, and here were some of the ideas. They said maybe something is concave up if it has a local min. And we're going to abbreviate concave up as CU. So if it has, oh, we shouldn't say it, we should say F has a local min. I'm not saying any of these end up being our definition, but they certainly kind of make sense based on what we see there. Another one was concave up if f goes from decreasing to increasing. Another one was concave up if f prime goes from negative to positive. What do you think? That's a prime there. How about concave up if f double prime is greater than 0? That's certainly true there. Or how about concave up if f prime is increasing? Seems like another good candidate. How about concave up if all tangent lines of the function fall below the function? Is that true here? That even if you extend this tangent line out, the function will never go below that tangent line. So all tangent lines of f are less than or equal to f. Of course, they wouldn't be strictly less than because they'd have to touch the function at some point, the point where they're tangent. So that's another idea. Or another one could be concave up if it's shaped like a particular kind of concave up, a concave lens or convex lens. And the idea here, how can we say that a convex lens has a different shape than a concave lens? If I pick any 2 points in a convex lens and draw the line segment between them, do you agree that that line segment will stay within the lens shape? Here I just chose 2, but it's true for any 2 points in that convex lens. If I choose any 2 points in the concave lens, sure, for some of them, the line segment between the 2 points will stay in the lens. But if I chose a point here and a point here, then that line segment goes outside the shape. So we could do the same idea here, but pick maybe a point here and a point here. So pick 2 points on the function, draw the line segment between them, and if that line segment stays on or above the function, then maybe we say it's concave up. The function is concave up. So we could say concave up if for any 2 points on the function, the line segment connecting them stays on or above the function. So hopefully you can see that is related to the shape we talked about here, up here, and you could see how to translate all of these to a concave down kind of context. So, not to spoil the fun or anything, but the first few here end up not being what we want to do. So these 3 end up not being what we want to do. Some books do this one. Our book does this one. And other books do these 2, this one or that one. So we're going to go with what our book says, concave up if f prime is increasing. It's worth your time, I think, to go, once we talk about a few more things in being concave up, concave down, to think, why do these definitions not end up being what we want? So maybe we'll come back to that later. All right, our next video will be trying out these definitions on some different functions.